The last talk this morning is by Professor Chen Kirsten from National Taiwan University. He's going to talk about revisit the statistical balancing.
The title of my this morning I'd like to talk about the idea of reviewing statistical downscaling methods, and because there are many different statistical downscaling methods, so I will only focus on the Richardson type weather generator, which use the monthly rainfall to downscale to for generation of daily rainfalls. And the other one is the bias correction, spatial disaggregation, or the so-called BCSD method. And the reason I like to do this is that I'm involved in the climate change study from the hydrological perspective. And so very often we need to use downscale data, but the downscale data need to preserve the statistical properties of the observed data. And so I was wondering whether different methods can really preserve very reliable statistical characteristic of the observed data. So even though we know there are two major categories of downscaling methods, like dynamic downscaling and statistical downscaling, and this morning we have several talks focused on dynamic downscaling, and also we have Professor Chen just mentioned some of the BCSD methods they applied for statistical downscaling. And so this is the different methods fall into the category of statistical downscaling, including regression approach, which is very straightforward. And also, there are also people who use change factor approach, which simply assign certain degree of changes to individual parameters. And then the stochastic weather generator, especially the Richardson type, I will give an example of assessment of its performance using stochastic simulation, and then the BCSD method. And also for my own research, I also developed a stochastic storm rainfall simulation model that can downscale, or that can generate sub-daily and also hourly rainfall data. But I will focus on these two methods this morning. And the weather generator is a statistical model used to generate a realistic daily sequence of weather variables. It can be applied to temperature, and also it can be applied to precipitation. And the Richardson type weather generator for daily rainfall generation, the process is divided into two sub-processes. The first one is to consider occurrences of rainfall events or daily rainfall. And for example, if we consider a wet day, if that day is if that day has a certain amount of rainfall, or we can consider another day which is dry without any rainfall. So it is the process of wet to dry or dry to wet. And usually they use a Markov chain process to consider the occurrences of daily rainfall. And the other process is the amount process, and that determines how much rainfall will occur if one day is determined to be a wet day. And this Richardson type weather generator is widely applied in many regions, and also over a range of climate impact sectors. And publication, you can find a lot of publication that can be traced back into 1960s. And so for the occurrences process, we need to first, based on the historical data, we calculate the probability, the conditional probability of wet day if the previous day is also a wet day. And also we can calculate the probability of a wet day if the previous day is dry, and then we can calculate this to probability based on this too. So it's just a very simple Markov chain process. We generate a sequence of wet or dry days, and we can have consecutive days of wet days, a consecutive period of wet days, or we can have a very long consecutive period of dry days. And after that, we use the random number generation for assigning rainfall amount to individual wet days. And for this process, we assume each individual daily rainfall is independently and identically distributed. So we can use the random number generator. For example, we can assume the exponential distribution, or we can assume gamma distribution. And then we generate a four months daily sequence. And this needs to be conducted for each individual month. So those probabilities were calculated dependent on individual months. And then many applications of the Richardson type weather generator also evaluate its performance based on, for example, in this slide, you can see that the top panel represents the evaluation of the temperature. The blue dot here represents the, this is the observed, blue dot, no, this line represents the average, monthly average of temperature from the historical data, and the blue dot represents the mean value based on our simulation, and this result is based on 100 simulation runs. So each individual month you can find the mean value and also this, its box plot, and we can see that the mean value based on simulation result are almost identical with the observed monthly average. So we can see that regardless of lower, medium, or higher temperature, and also for rainfall, the mean value by the weather generator are very close to or almost identical to with the observed mean values. But the question is that if the target data are daily temperatures or daily rainfalls, why were the validation conducted using data of monthly scale? Because we want to downscale to daily scale, and how then we should verify or validate the results based on daily scale instead of the monthly scale. And so this is the problem. So I conducted some stochastic simulation to see if we evaluate the method based on daily scale, what are their performances. And the concerns from hydrological perspective is that the method, the Richardson type method, cannot identify or characterize rainfall events because the rainfall occurrences are controlled by Markov process. However, the daily rainfalls are independently generated, and that leads to difficulties in defining individual storm events. For example, duration, for Richardson type weather generator, the durations are controlled by Markov process, but rainfalls of individual days are the same event, which means that if we have a period, a consecutive period of wet days, then daily rainfall within that period are independently generated. And so if we consider an event, but here we have within that event, daily rainfall are independently generated. So it appears that we have the with respect to the event duration, yes, we have event, but with respect to rainfall, it seems that we generate events, and every event has only 1 day duration because the rainfall, the daily rainfalls are all independently and identically distributed. So this caused the problems of not being able to represent the storm characteristics by using the Richardson type weather generator. And also the properties of occurrences, frequencies, and storm duration are dependent on storm type. For example, in Taiwan, in the summertime, we have typhoons, and typhoon usually have a duration of several days. And the Richardson type simply cannot generate results that can characterize the event total rainfall with that kind of duration. So here is one example. I use the data from the Kaohsiung station. This is based on 20 years of daily rainfall in August. And I calculate that one autocorrelation coefficient of daily rainfall in Kaohsiung. And so this is the daily rainfall of 1 day, and this represents the daily rainfall of the next day. And I found that that one autocorrelation coefficient is about 0.4. If this point, I consider that as an outlier, but if this point is included in the analysis, that one autocorrelation is about 0.4. But if this point is removed, then we can see that the that one autocorrelation coefficient are raised to about 0.5. So it indicates that the that one autocorrelation coefficient or the correlation between two daily rainfall are important, and this property cannot be represented by the Richardson weather type generator. And so I conducted the Richardson weather type generator, and then you can see that this is the result of the daily rainfall simulation based on Richardson type, and it doesn't show any daily rainfall autocorrelation. Okay. So this is one drawback of the daily Richardson weather type generator, and also I calculate from the historical data and also based on the Richardson type weather generator simulation result, I calculate the cumulative distribution function of the event duration. And as you can see here, in August, it is not likely that we will have an event that with a duration of, say, more than 6 or 7 days, because about 80% of the events have duration shorter than 6 days. But the simulation results give you higher probability of having longer duration of the simulated storm events. So it indicates that if we are concerned about the storm characteristics, then the Richardson type weather generator is not capable of reflecting that results. So the suggestions for using the Richardson type daily rainfall generator is that it probably can be applied to areas dominated by short duration storms, and because they tend to have relatively lower lag 1 autocorrelation coefficient. Or in many applications, we need to use daily rainfall for rainfall runoff modeling. And if we want to use the runoff, if we want to use the daily rainfall to generate runoff, then the application which focus on runoff volume may be more useful. The method may be more useful for runoff volume. But if we want to consider the peak flow rates, then the results from Richardson type weather generator is not very useful, and it should not be applied. And the next point is that the larger watershed with longer time of concentration, for example, a large watershed with several days of time of concentration, maybe we can use that daily rainfall results from weather generator for rainfall runoff modeling, because the peak rainfall is not highly dependent on the daily rainfall variations. So those are the suggestions for using the Richardson type daily rainfall weather generator. And as for the second method, the BCS method, for the BCSD method, there are two steps. The first step is to conduct bias correction, and the bias correction are performed on the GCM grids. And then the next step is to spatially interpolate the results on GCM grid to finer scale, and that is called the spatial disaggregation, and they are conducted onto finer scales. And this slide demonstrates the steps of statistical downscaling, and basically, as Professor Chen just mentioned, it is the quantile mapping method. So, for example, here we have this represents the cumulative distribution, and this represents the, for example, the rainfall amount, and therefore we have the cumulative distribution from GCM output, and we have cumulative distribution this is the cumulative distribution of the GCM output, and this is the cumulative distribution of the observed data. And so we first find the cumulative probability or the quantile of this amount, and you assign the value with the same cumulative distribution function of our historical data to correct the bias. So this is the a quantile mapping function for bias correction. And so after we conduct bias correction, then we, this is the first step, and then we calculate a factor which represents, for example, for precipitation, we calculate the bias corrected value, the ratio of the corrected value to the long-term average, and that gives you a factor field. For example, here we have the observation means, and we calculate the after the bias correction, we calculate factors which is in GCM grid scale. As you can see here, so we have, for each GCM grid, we have a factor, and then we conduct spatial interpolation to finer scale. And for example, originally we have 2-degree GCM grid, and then we interpolate the factor to grid interval of 1/8 of a degree, and then we multiply the factor by the local expected value to generate the downscale data. So this is the second step, the spatial disaggregation of the BCSD method. But one of the major concerns is that by interpolate from coarse scale to finer scale, in fact, we, in my opinion, we do not reduce the, we do not downscale the spatial resolution at all, because here we calculate the factor based on 2-degree grid, and the resolution is 2-degree. But the spatial resolution, we simply interpolate to finer interval, but interpolation to finer interval does not imply that we reduce the, we increase the spatial resolution, because we can always use the 2-degree factor interpolate to very, very fine interval, but the interpolated factor is still in 2-degree resolution. So that's the major concern of my application. So I conducted the stochastic simulation to demonstrate that the spatial disaggregation in the BCSD method actually does not improve the spatial resolution. So here I used X sub 0 represents the baseline period observed data, and X1 represents the projection period observed data if we can observe that. So I assigned two different distributions. They only differ in their expected values. And for projection period, I also have y sub 0. That represents the GCM. I'm sorry. This is, y sub 0 represents the baseline period GCM output, and y sub 1 represents the projection period GCM output. And as you can see here, they also only differ in their expected values. And the difference between y sub 0 and x sub 0 represents the performance of the GCM. And as you can see here, the relationship between y sub 0 and x sub 0 and y sub 1 and x sub 1 are consistent, which means the performance of the GCM is consistent from the baseline period to the projection period. The GCM is the GCM output underestimates the observed data, as you can see here, by comparing their expected values, and the performance are consistent from baseline period to projection period, and also I assume the data are all normally distributed, and then I conducted simulation using different lengths of periods from 30 years, 50 years, and 100 years. But for our climate change study, usually the baseline period is about 30 years. But for comparison, I simply try different lengths of different periods. And also because I like to study the asymptotic properties of our estimation, so I use a large number of samples. In this study, I conducted simulation for 100 samples for each record length. And so this is this slide shows the cumulative distribution function of the simulation results. And as you can see here, the black line here represents y sub 0, and that is the GCM output of the baseline period, and Y1, the thin red line here represents the GCM output of the projection period. And again here, the green line represents the CDF function of the observed data for the baseline period. And if we conduct bias correction for the baseline period, then the GCM output will be corrected. The GCM output will be corrected to become identical with the observed data, and the thick red line represents the results of bias correction for GCM output. And so if the projection period GCM output is bias corrected, then it will become this cumulative distribution function. And the blue line, the thick blue line, represents the observed data in projection period, if we can really observe that. So you can see that there are differences. And based on these simulation results, I want to analyze the quantiles from 25%, 50%, 75 to even 90, 95, 99% quantile of the bias correct results. And you can see that X1, the red line, represents the observed data of the projection period, and the blue line represents the bias corrected GCM output in the projection period, and for different quantiles. And the interesting is that for small quantiles, the bias corrected GCM output tend to be smaller than, bias corrected GCM output tend to be larger than the observed data. But for higher quantile, as you can see here, the 99% quantile, the red line here represents the observed data of the projection period, but you can see that the blue line all fall to the left, this 99% quantile. So, and this is for sample size of 30, and which means we simulate a period of 30 years. And for simulation of 50 years and 100 years, they all show the same result. So it indicates that the bias correction by the BCSD method tends to underestimate the high quantiles. And also I conducted the evaluation of the spatial disaggregation, but because of time limit, I will skip some of the simulation here. It only, time's up. It shows that this is the point data, which means that we do not upscale. But if we use higher, larger resolution, it indicates the spatial correlation will be raised to very high. So the spatial autocorrelation change with the grid scale. So and also I use these results. This is the results by let me see, by Horton, and this panel shows the observed long-term average, and this is the downscale data by the BCSD method. And they look similar, but if you look into the details, I show those. This is the this slide. I zoom in the area, and again we can zoom in this area, and we can compare the differences. So this represents the results of spatial disaggregation. This represents the observed data, and this represents downscale data. And if you compare these two, you can find much more details here. And it indicates that the spatial disaggregation by the BCSD method actually reduced the spatial variation, because it does not reduce the resolution. You know, the spatial the factor of the spatial disaggregation of the factor does not reduce the resolution. For this application, the factor was still in 2 degrees resolution, even though the factor were interpolated to half 1/8 of 1 degree. Okay. And also you can compare this. This is the downscale result, and this is the observation result, and you can find much fine spatial variations in this area, and also even in this area, and even here. Okay. Because of time limit, I'll skip this one. So I'll give suggestions and remarks. The BCSD method tends to underestimate high quantiles. And for spatial disaggregation, BCSD method results reduce both the local and spatial variabilities. And therefore, the method is useful for assessment of long-term climatology, or the mean values. But if we want to assess changes in extreme, then we need to exercise extra caution. Thank you very much, and that concludes my presentation.
Thank you. Any question? Actually, your suggestion for the Church type weather generator for the larger scale the watershed. So, but in the case actually larger scale watershed means actually we need some more weather stations actually to consider the spatial distribution. But the Church type actually has some limitation to consider the spatial clearance. So actually, if we really want to apply that approach to the larger watershed, actually we need to keep the spatial clearance, because if there's a rain in a specific day, if there's a rain for this station, but if there's no rain on the near station, actually the peak flow can be underestimated in that. So
your question is about the spatial variation, but the Richardson type with a generator is only for the time, the temporal downscaling. So for spatial interpolation, that's maybe another work. But for the application of Richardson type, they only generate daily rainfall at each individual site.
Any other questions? Okay. If not, sorry for keeping the time very badly, but just as you said, all the speakers this afternoon